Hi, I'm Cameron. This is Lab 4 Oscillations for Physics 1. The purpose of this lab is to model the movement of the spring mass system, observe the energy principle, and compare the oscillations of the experiment and model. Some of the fundamental principles of this lab is Newton's second law, which explains that an object will accelerate if there is a force acting on it. In this case, we will use the velocity update formula, which will help us find the new velocity of our system. Another fundamental law is Newton's first law, which states that an object will stay in motion until a force acts upon it. This includes the position update formula, which will help us find the new position of the spring mass system. The last principle is the energy principle. This states that the total energy of the system is the sum of the work and heat of its surroundings, but it's also the sum of the change in energies of the system. The energy equations for this experiment is the gravitational potential energy, which is the mass times the acceleration due to gravity and the change in position. Next is the kinetic energy equation, which is 1/2 mass times velocity squared. And last is the spring potential energy, which is 1/2 the spring constant times s squared, s being L minus L naught. Here is a diagram of the spring mass system. We see that there are two forces acting on the system, that being spring force and the force of gravity. The reason I'm using these models and principles is so that I can accurately observe the energy and oscillations of the spring mass system. The initial conditions of the experiment are as follows. Mind you, some of these are given in the spring analysis video. Most importantly though, the ball's position is negative 0.105 and negative 0.646 meters in the x and y directions. The ball's velocity and the time start at 0. The system is the ball, spring, and earth, which means that there is nothing in the surroundings. To preview the results of the experiment, the total energy change in the system is 0, and the position graphs are similar to those of the model. Next is the video. The initial conditions were entered before this part of the code. In this part of code, some of the following variables were given in the video. But most importantly, the variables k is 6.83 and L naught is 0.123 as stated in the video. L is the change in position of the ball and the spring, and L hat is L divided by its magnitude. S is the magnitude of L minus L naught, and my energy variables are K, UG, and US. These values are the equations I explained in the principal energy slide, and E is the sum of all of these energies. For the loop, I define the initial energies of the system as the energy variables I made prior. I define the force of gravity to be m times negative g in the vector form, and the spring force is negative k times s times L hat. Next, I use the velocity and position update formulas to update the velocity and position of the system, and lastly, I redefine the key spring variables so that they can be updated using the loop. I also redefine the energies I found before the loop, and using the initial energies I defined in the loop, I calculate the changes in energies by subtracting the final energies by their initial energies. Here are my results. The result of my experiment yielded that the change in total energy was 0, indicated by the orange line. These graphs compare the x and y positions of my experiment and the model, and as you can tell, they are quite similar. Comparing my experiment to the model, both do not begin at the origin. Similarly, both show consistent oscillations throughout the graph. The most important difference is that the amplitudes of the model and experiment do not match in most places. So, is the energy principle satisfied? Yes, the energy principle is satisfied as seen earlier in the energy graph. All energies are conserved, meaning no energy leaves the system and energy is constant throughout the experiment. On the graph, the constant oscillations in the energy show this conservation. Additionally, the fact that the change in total energy is 0 shows that the initial and final energies are the same, so no energy was added or subtracted. Next, the question is, what are the periods of oscillation of the x and y directions, and compare them. The x position oscillation is 1.582 and the y is 1.709 seconds. This was found by averaging the oscillations of the tracker data. The difference in the data is due to two things. One, there are no accounted forces acting in the x direction, only the y. Additionally, there are some unaccounted forces acting on the system, like drag force, that could have possibly changed the oscillations of the system. Some coding errors in the experiment could be due to not considering other forces acting on the system when constructing my code. Another coding error could be starting the velocity at 0, when in reality, the ball didn't exactly start at 0. A data error could be that the choice of frames could have given different and or less accurate times for the positions. Thank you for watching.